In the last chapter, we learned about lattices. In this chapter, we're going to use lattices to perform what's called data flow analysis. Data flow analysis is a technique that will allow us to determine some properties of programs, including the signs of variables, which expressions can be eliminated, and which ones can be reused. The general formula for doing all of these different forms of analysis will be as follows. We'll take in a control flow graph and a finite height lattice. We'll assign a constraint variable for every node in the control flow graph, and this constraint variable will take on a value of one of the elements in the lattice. For every node, we'll define a data flow constraint, which will constrain the value of a particular variable based on the values of other variables in the control flow graph. This all may sound a little abstract right now, but we'll see how it's instantiated on all of these different problems. Our first example of a data flow analysis will be sign analysis. In the sign analysis problem, our lattice will be the map lattice from variables to signs. And for each control flow graph node, we'll assign a constraint variable denoting an abstract state that gives the sign values for all variables at that point in the program immediately after. If there are n nodes in our control flow graph, then n states will represent all of the information for our CFG nodes. But how do we determine the value of these constraint variables? We'll start with a few auxiliary definitions. We'll define this function join of v. So join is a function that'll take in a control flow graph node, and it will sort of combine abstract states from its predecessors. So it's going to range over all of the predecessors of that node and take the least upper bound of those constraints. So say we're looking at the program represented by this control flow graph. One of the nodes is a equals c plus 2 at the very bottom. This node has a constraint variable associated with it, represented by a equals c plus 2 in double brackets. And to compute the join of this constraint variable, we'll look at the node in the CFG and look at all of its predecessors. So in this example, it has two predecessors, c equals b and c equals -5. We'll find the constraint variables associated with both of these predecessors and take their least upper bound. That will be the join of the constraint variable of this bottom node in our CFG. The way we determine the value of a constraint variable at a particular CFG node will depend on what exactly the type of that CFG node is. So for example, if we have a CFG node with an assignment in it, we'll use the following rule to populate the constraint variable for that node. So the constraint variable of an assignment node v will be join of v, which means we'll go through each of the predecessors of this assignment and find their least upper bound. The least upper bound will be an element of a map lattice, so it's going to be some kind of mapping, and we're going to take that mapping and change out the value of x. And that kind of makes sense because after this node, we just change the value of x to e. In particular, we're going to change the mapping of x from whatever it was to eval of join of e of e. Eval is a function that will just determine the sign of e in the current state of the program. So for example, if e is just a variable and we call eval on it, we're going to look up the sign of that variable in the state of the program. If e is the input function, we're going to return top because we won't know the sign of e. If e is a binary expression, we'll abstractly evaluate both sides of that expression and then abstractly combine them. This op with a little hat on it represents combining abstract values together. We use these tables to abstractly combine values. Each rule makes sense intuitively. For example, if our expression was e1 plus e2 and we didn't know the sign of e1 and we didn't know the sign of e2, we wouldn't know the sign of the expression as a whole. On the other hand, if we knew that e1 and e2 were both positive, we would know that the expression as a whole is positive. So that was the rule for assignments, and we'll have a different rule for variable declarations. For variable declarations, we'll just initialize our state to have no information for each of our new variables. So if we're declaring variables x1 through xn, we'll use our old state and then also add in the information that x1 through xn are mapped to top because we don't know their signs. For all other nodes, we'll just use the rule v is equal to join v. So that represents just passing on the information of all the predecessors unchanged. Then for the program as a whole, we'll have a system of equations. If there are n CFG nodes, we'll have n equations, and that might look something like this. The lattice and the constraints form a monotone framework. This is because the right side of our constraints correspond to monotone functions. We can combine together the functions af1 to afn into a master function, call it af, which will just return a tuple of af1 through afn applied to their arguments. We'll obtain the results of the analysis for the given program by computing the fixed point of af. A second problem we can instantiate our monotone framework on is that of constant propagation analysis. So in constant propagation analysis, we want to determine the variables in a program that have constant value. Each time we perform a data flow analysis, we'll need a CFG and a finite height lattice. So the CFG for constant propagation analysis will once again be the CFG of the program, but the finite height lattice will be flat of z, where z is the set of all integers. So that's this lattice. It has a bottom element, a top element, and all of the integers. And in sign analysis, we only had 3 states in the sort of middle layer of our lattice. And in this one, we have infinitely many. This is still a finite height lattice because there are infinite elements, but the height of the lattice is still 2. This analysis will otherwise go exactly the same as our sign analysis. We'll compute joins over each of our CFG nodes and then compute the fixed points. And this will represent the end result of our analysis. The only difference is the way we abstract away our operators. With this lattice, we can be more precise because we abstract away less information. To abstractly combine 2 elements of our lattice using an operator, we'll use the following function. If the elements of the lattice that we're combining are numbers, we'll really just use the operator. So for example, for 4 plus 2, we'll really just add 4 and 2. If, on the other hand, either of the elements is bottom, we'll say it's bottom, and if either is top, then it's top. So as one of the last steps in our data flow analysis, we've been computing the fixed point of a function. And we saw an algorithm for computing fixed points in a previous chapter. That algorithm was naive, and there are actually better ways of computing fixed points. Moving towards more efficient algorithms, we can look at this round-robin algorithm. Our round-robin algorithm will take in n different functions and start by initializing x1 to xn to bottom. And it's going to perform this loop once again of checking that x is not equal to f of x, but it's going to kind of perform each update of x sub I with x sub I gets updated to f sub I of x sub I independently. The round-robin algorithm makes use of the fact that each constraint function can depend on only a subset of variables and will remain unchanged for most iterations. The round-robin algorithm performs the computation differently, but in the end it'll still give you the same result as the naive fixed point algorithm. As a step towards improving the round-robin algorithm, we can recognize that the order of iterations of I from 1 to n is irrelevant. The only thing that's important is that each constraint function is applied again and again until a fixed point is reached for all of them. We can capture this intuition with the chaotic iteration algorithm for computing fixed points. So instead of looping over 1 to n, we choose I non-deterministically from 1 to n. The efficiency and termination depend on how I is chosen in each iteration, so that makes this algorithm less practical. We're not even guaranteed that this algorithm will terminate because we could keep on choosing I to be something that's already converged and not make any progress. A practical variant of the chaotic iteration can go as follows. We'll start by recognizing that each f sub I will only read the values of a few other variables, and you can represent these dependencies as a map. So dep is a map of nodes to a subset of other nodes. So dep tells us which subset of other nodes occur in a non-trivial manner on the right-hand side of their data flow equations. And with that information, we can make this work list algorithm. So we're going to start by initializing x1 to xn to bottom, and we're going to have this w, which is the set of nodes. And while w is not empty, we're going to take an element out of it. We're going to compute this f sub I of all of our x's. If y is not x sub I, then we'll update x sub I to be y. And since we performed this update, we'll take each of the dependencies and add those back into our work list. Live variable analysis will determine if a variable is live. A variable is live at a particular point in the program if it will be read from before it is written to. So why is this interesting? Because if a variable is not live, that means you don't need to store its value at all. That's because it's going to be written to before it's read again. So its current value really doesn't matter at all. Once again, with data flow analysis, we'll need a CFG and a lattice. And this time our lattice will be the power set lattice, where elements are the variables occurring in the given program. So for example, in this program, we have variables x, y, and z. And so the lattice representing abstract states is the power set x, y, z. The CFG of this program will be as follows. And for every CFG node, we'll add a constraint variable. This constraint variable will range over the elements of the lattice, which is this power set of x, y, z. And so the value of the constraint variable will represent the subset of variables that are alive at the program point before that node. The join function for this analysis will be unioning together all of the successor nodes. Keep in mind the successor node constraint variables are sets, and so we're basically taking a node v and unioning together all the sets at later points in the program. The most interesting constraint rule will be, once again, for assignments, and the rule will be as follows. V equals join of v without x unioned with the vars in E. So this rule represents the fact that the set of live variables before an assignment is the same as the set of variables after the assignment, except the variable being written to is no longer live, and the variables in the expression are live. For branch conditions and output statements, our rule will be v equals join v unioned with vars of E. So this represents the fact that the variables live before a branch or output statement are the same as the ones after it, except the variables in E were live before, even if they weren't live after. And for variable declarations, we have the following rule. So the variables live before this declaration are the same as the ones live after it, except we'll take out x1 through xn if they exist. And for all other nodes, we have this very simple rule. Next up, we'll do available expression analysis. Available expression analysis will determine which expressions are available at a given point in the program. And an expression in a program is said to be available if its value has already been computed earlier in the execution. The lattice we'll use will be the power set of all expressions in the program, ordered by reverse subset inclusion. So for example, if we have this program, you can see there's expressions a plus b, a times b, y is greater than a plus b, and a plus 1. So that's the set of expressions in the program, and our lattice will be the following. A particular value of this lattice represents what expressions are available at a program point. So at the very top of the lattice, we would have that no expressions are available. At the very bottom, we have that all expressions are available. And in the middle we can have different subsets of expressions are available. This analysis can be useful for program optimization because if we know an expression has already been computed, we don't have to compute it again. So we'll now define the data flow constraints. Our constraints will model our intuition that an expression is available at a node v if it is available from all incoming edges or is computed by v, unless its value is destroyed by an assignment statement. So join of v will be the intersection of all the predecessors. So it's not enough for a expression to be available in one of the predecessors of a CFG node. It needs to be there in all of them. Otherwise, it might not be there in the current node. Assignments will be modeled as follows. So we're unioning together join with this function exps of e, and then we're taking those together and applying this function down of x on it. And down x removes all expressions that contain the variable x, and this function exps is defined as follows. It's basically just collecting all non-trivial expressions. The rule for branch conditions and output statements are as follows. We're just taking all of the expressions that are available in that statement. And for all other nodes, the only expressions that are available are those that are available in all other predecessor nodes. So that's why we can just use the join function here. Somewhat similarly to available expression analysis, we can perform very busy expression analysis. Very busy expressions are expressions that definitely will be evaluated again before its value changes. Unlike with available expression analysis, this is a forward-looking analysis. So an expression is very busy depending on whether or not it'll be used in the future. It's available depending on whether or not it was computed in the past. Our join rule for very busy expression analysis will reflect that difference. We define join of v as the intersection of all successor constraints. Our assignments will be modeled with the following constraint rule. The constraint variable v for a CFG node that is x equals e will be join of v and then this down arrow function union together with the non-trivial expressions in e. So again, join was the intersection of all successor nodes. So we're saying we'll take all of the non-trivial expressions in all successor nodes and union them together with the expression that we're assigning to. The constraint variable of an exit node will just be the empty set, because no expressions are very busy at exit nodes. The rest of the rules for constraint variables will be the same as for available expression analysis, including those for branch conditions and output statements. This kind of analysis will aid compilers in doing something called code hoisting. So if you look at this example program, we declare three variables, set one of them to input, a is x minus 1, b equals x minus 2. Inside the loop, we keep on outputting a times b minus x. And this expression is very busy for that reason. So it keeps on being needed. And for that reason, we could hoist it outside of the loop. That would transform the program into the following. Say we're looking at a variable at a particular point in the program, and we want to know where in the program this variable got its value. Well, it certainly got its value in some assignment statement, but which one? Reaching definition analysis tells us this. For example, for this input program, our state lattice will be the following. So this is just the power set lattice with each element of the set being an assignment that occurred somewhere in the program. The constraint variable for a node will be the set of assignments that may have set the value for the variables beyond this point in the program. Since we want to know which set of assignments may have influenced the values of the variable going forward in the program, our join function will reflect that. So join of v will be defined as the union of all predecessor nodes of v. Our constraint rule for assignments will be as follows. V equals join of v, down arrow x, union together with the value x equals e. And so the down arrow x means removing all the assignments to the variable x. Intuitively, this constraint is just saying that after a particular assignment, you know that the variables in the program could have been assigned at any of their previous assignments except for x, which was definitely assigned at this point with the expression x equals e. For all nodes besides assignments, we have the constraint rule v equals join of v, and that's just saying that if we have a statement that's not an assignment, the variables still got their values at whatever assignments they previously got their values from. One thing that's cool about this analysis is that we can use it to construct what's called a def use graph. So in a def use graph, edges will go from definitions to possible uses. So for our example program, this will be the def use graph. So at the very top we have x equals input, and then there's an arrow going out of it to the expression x is greater than 1 and y equals x over 2. So that captures the intuition that the value of x in the expressions x is greater than 1 or x divided by 2, it got its value in the assignment x equals input. Every analysis that we've discussed so far is going to either be a forward analysis or a backward analysis. It's also either going to be a may analysis or a must analysis. So let's talk about what each of these terms mean. So a forward analysis is an analysis that at every program point will compute information about past behavior of the program. So this is somewhat confusingly named, but the term forward isn't referring to the information that's being stored at every node. It's about the way in which the analysis proceeds. So the analysis starts at the entry node and then propagates information forwards in the CFG. And in these analyses, the join function is over all the predecessor nodes. An example of a forward analysis is reaching definitions and available expressions analysis. A backwards analysis is just the opposite of a forwards analysis. So at every CFG node, we're combining together information from successor nodes. So the information is sort of flowing backwards. In a may analysis, we describe information that might be true. That's why it's called may analysis. And this is also called an over approximation. So examples of what might be true, so a may analysis, are live variables analysis and reaching definitions analysis. So if you remember, in live variables analysis, we found what variables might be live, not which ones were certain to be live. Also in may analysis, the constraint function used the union operator to combine information. By contrast, a must analysis describes information that is definitely true. This is also called an under approximation. So in a must analysis, the join function will use the intersection operator. Thinking in terms of forwards, backwards, may, and must will help us when we're designing new analyses. This is because in every forward analysis, we know we'll be combining information from predecessor nodes. In every backwards analysis, we know we'll be combining information from successor nodes. In every may analysis, we'll be unioning together joins, and in every must analysis, we'll be intersecting together joins. So now let's think of the problem of initialized variables analysis. In this analysis, we're trying to determine which variables are definitely initialized. So since we want to know what's definitely true at any given program point, we know we'll be making a must analysis. And in a must analysis, we'll be using the intersection operator. And since which variables are initialized depends on what was previously run in the program, so previous statements, previous CFG nodes, we know we'll do a forward analysis, and our join function will be over predecessor nodes.
If you think about it, coming up with the join function was most of the work in describing how to perform the analysis. All that remains to be done is describing constraint rules. This one's pretty straightforward. You can imagine you just use the join function and for assignment nodes, you also add in the variable being assigned to.